Hello everyone, I'm Hiroshi Kagawa from Hiroshima University. In this video, I'd like to talk about fully pipelined architecture for simulated annealing-based QUBO solver on the FPGA. This is a contribution of our research. First, we will propose two local search algorithms based on the simulated annealing. Second, we will propose a new fully pipelined FPGA architecture for QUBO solver that performs both algorithms. This implementation supports a 1 kilobit QUBO problem with 16-bit weights, and we can search for up to 600 giga solutions per second using this system. First, I'd like to talk about QUBO. QUBO is an NP hard problem. An input of QUBO is given by an n-symmetric matrix W called a weight matrix, and the goal of QUBO is to finding an n-bit binary vector that minimizes this function. For example, if we have this weight matrix and we set a vector as 1, 0, 1, 1, the value of the energy is -8. This value is the sum of the element highlighted in blue in the matrix. So why is the QUBO problem important? Because many NP problems can be converted to QUBO, and a QUBO solver can be used as a solver for a wide range of combinational optimization problems. For example, maximum cut problems and traveling salesman problems can be mapped into the weight matrix. Next, I'd like to talk about a local search in QUBO. A local search is a good heuristic method for solving QUBO. For an n-bit vector x, let's define a function that outputs the vector which is flipped the case bit. For example, we have x equal to 1, 0, 0, 1. By flipping x1 from 0 to 1, we obtain f1 of x equal to 1, 1, 0, 1. This figure illustrates a local search in QUBO. We can use the function to obtain neighbor solutions and search for the best solution by continuing the transition. Next, I'd like to introduce an efficient computation technique for a local search in QUBO. In this local search, we must evaluate the objective function for each solution. In this case of QUBO, it is the energy. As you can see from the objective function of QUBO, the computational cost is too large, so we should elaborate the approach of the local search. Let's consider the difference of the energy donated by delta k of x. For example, delta 1 is computed by the element highlighted in green in this matrix. Since the difference between x and fk of x occurs only in flip bit xk, so we can compute the value of delta by the weights in one row and one column of the matrix. And we can evaluate the neighborhoods efficiently using the incremental computation technique. Furthermore, we can also use the incremental computation technique for each delta. Let's consider the difference of delta I after xk is flipped. Since the difference between x and fk of x occurs only in flip bit xk, so each value of delta can be used again by changing the term only which are affected by the bit flip. More simply, if I equal k, we just reverse the number sign of the delta. If not, we just add or subtract two weights written in yellow in the matrix. After that, we can reuse the value of each delta. So a local search in QUBO can be performed efficiently by repeating step 1 and step 2. In step 1, we select a flip bit in some way and evaluating the objective function. In step 2, we update each delta using the incremental computation technique. Next, I'd like to consider how to select a flip bit in a local search. I think one of the simplest methods is greedy algorithm. In this algorithm, we continue to select the best transition among neighborhoods. However, it is often difficult to find the best solution of QUBO, because the solution space of QUBO often has local minimums. If we continue to accept the transition only that decreases the value of the energy, the solution will eventually get stuck at a local minimum, as shown in the right figure, and the local search will be stopped. So, in this study, we propose two local search algorithms to obtain better solutions. First, I'd like to introduce max-min-SA algorithm based on simulated annealing. In this algorithm, we narrow down the transition using a threshold computed by this formula. We select a flip bit at random among the bits which satisfy this condition. This formula includes the temperature parameter which decreases over time. So flip candidates that increase the energy function gradually disappear with a decrease in the temperature parameter, and the local search shifts from random search to greedy search. In addition to this, the decrease is gradual, so we can move the solution closer to a global minimum while avoiding a local minimum. Next, I'd like to introduce positive min-SA algorithm. In this algorithm, we perform the local search without using parameter like temperature. We perform the local search with the proximity distance between the solution and the nearest local minimum. The difference between this algorithm and before one is that the threshold. We set the threshold to the smallest value of the positive delta. That has led to perform with the proximity distance like this figure. When the solution is far from the local minima, the candidates to be flipped consist of many candidates with a decrease in the energy and one or few candidates with increasing. Therefore, if we select a flip bit at random among flip candidates, the energy will decrease. When the solution is near a local minima, the majority of bits in the candidates have still negative. However, the energy increases with low probability. On the other hand, when the solution is in a local minima, all bits in the candidate have the value of the positive delta. Therefore, the energy always increases. From the above, when the solution is around a local minimum, the positive min-SA algorithm tend to escape from it. Why did we propose this algorithm? Because each algorithm has its own suitable solution space. Max-min-SA algorithm is good at exploring spaces with distinctly uneven surfaces. For example, if we convert to Max-min-SA algorithm is good at exploring spaces with distinctly uneven surfaces. For example, if we convert a max cut problem to QUBO, the solution space often looks like this. In contrast, positive min-SA algorithm is good at exploring spaces with rough surfaces. For example, if you converted a TSP to QUBO, the solution space often looks like this. We can obtain a better solution using a suitable good algorithms. From this slide, I'd like to introduce the FPGA implementation that performs our proposed algorithms. In this implementation, we perform m instances for a single QUBO problem. The instances consist of the QUBO solution, the energy, and the delta of delta in each bit. Each instance is dequeued from solution pool one by one for each clock. After that, this goes through each circuit in turn and flip operation is performed. Finally, each instance is enqueued to solution pool. We perform our proposed local search by repeating this operation. Next, I'll show the structure of this circuit. Firstly, each instance is dequeued from solution pool one by one. Secondly, the threshold which narrow down flip candidate is computed using selector and comparator, and then a flip bit is selected at random among flip candidates using a binary tree structure selection circuit consisting of selector. Thirdly, the solution, the energy, and each delta is updated that based on the flip bit using this circuit. Finally, the instance is enqueued to the solution pool. Also, all proposed circuits are designed with a fully pipelined structure. Next, I'm going to show experimental result. In this study, we implemented the proposed circuit in V09P board equipped with the Xilinx Vertex UltraScale Plus FPGA. The resource usage and the clock frequency are as shown in the table. In this circuit, the memory usage is high because the weight matrix of QUBO is stored in blockrams. Next, I'm going to show the performance of our proposed algorithms. In this study, we converted several existing benchmarks to QUBO and performed our proposed algorithms. The results are shown in the table. According to the table, we can find the best solution or almost best solution using our proposed algorithms. Also, the results show that the search performance varies with each algorithm. Next, we observe the behavior of the proposed algorithms. These figures show the transition graph of the best solution by repeating the flip operation for max cut problem and the TSP. We can see from the left figure that the solution of the max-min-SA algorithm for the max cut problem is getting closer and closer to the optimal solution while repeating the flip bit. On the other hand, the improvement of the solution of the positive min-SA algorithm is stopped at early stage. In contrast, the right figure shows that the positive min-SA algorithm found almost the optimal solution for the TSP by gradually improving the solution. These results suggest that the algorithm needs to be selected depending on the problem to be solved. Next, we evaluate the search rate. That is the number of the total solutions searched by a system per second. For 1 kilobit program, our proposed system attains 600 giga evaluations per second, which is 30 times faster than this work. On the other hand, the GPU system is approximately 2 times higher than that of our proposed FPGA system. It is difficult to compare the performance of the FPGA and the GPU directly. However, since the GPU system uses 4 GPUs, while the proposed system uses only 1 FPGA, therefore the search rate of our proposed system is still high. In our work, we have presented a free pipelined architecture for QUBO solver on the FPGA and proposed 2 local search algorithms based on simulated annealing. The hardware implementation supports 1 kilobit QUBO problem with 16-bit weights. The implementation results show that the circuit can search up to 600 giga solutions per second. That's all. Thank you for listening.